Hello everybody, welcome to Cranky Calculus, where we are here to help take the edge off. Let's go over it with continuity here. Big thing about the continuity is that we are discussing it can only prove continuity at a point. We are not able to prove continuity on an interval. We can observe it in an interval, but we cannot actually prove it on the interval itself. So the definition of continuity is three things. Gotta make sure that if we have a function of f, we're talking about continuity at a point x equals c. We have to make sure that f of c is defined, the limit as x approaches c of f of x exists, and that the f of c is equal to that limit as well. So we're gonna go ahead and start to talk about types of discontinuity. We have removable, and that's going to real quickly just draw for you. That's an instance where we have a hole. Okay, there could be a dot there, but essentially we just were able to remove it. We have a jump. One of these guys right here where it kind of jumps up from graph to graph, and we have infinite, which we would know as a vertical asymptote. So just here's an example of one. Okay, and then also I kind of skipped a little bit, but continuity on a domain. We can only talk about continuity on inside the domain. We can't actually talk about it outside the domain. For example, if we have like a square root function, we can only talk about continuity for all 0 and positive x values. Okay, so let's go ahead and go to our first example right here. Determine whether the function f of x is continuous. You can see that piecewise function right over there to the right. So let's get cracking at it. So for this one, all we're going to do is, so the very first thing is we need to plug in f of 3. So we plug in f of 3. We actually have that defined. That is equal to 6. It's right there in the piecewise function. Second thing we are going to do here is we are going to find that limit. Now, since we are only with this piecewise function, it's kind of weird. What it is the function is that top piece everywhere except at that one little point. So since we're looking at the limit, we're going to be looking at the limit, which is going to be the top one. So the limit as x approaches 3 of f of x is equal to the limit as x approaches 3 of x squared minus 9 all over x minus 3. So we're looking at that limit individually. If you notice that this does factor nicely, the top turns into x minus 3, x plus 3. And these cancel out, so I'm actually able to plug this in, and then so we're going to get the limit as x approaches 3 of x plus 3, which does equal 6. So step 2 is good. So step 1 worked, step 2 worked, and step 3, f of 3, if you look at those two, step 1 and 2, does indeed equal the limit as x approaches 3 of f of x. You don't need this last part, but I'm just going to show you because it's going to be helpful to know that that equals 6. Okay. So let's go ahead and go into the last example here. Find the values at which x of x at which the given function is discontinuous. Identify discontinuity type. So again, it's super helpful to know here that we can only do this inside the interval, or sorry, inside the domain. We can't do anything outside the domain. So for A, it's really helpful to know what this looks like. This is actually going to be a semicircle. Okay, because how do I know that? Well, if I have x squared plus y squared equals 16, and I were to solve for y squared, I would get y squared equals 16 minus x squared. Solving for y, I would get plus and minus square root of 16 minus x squared. Since I only have the positive one, we only have a semicircle. So if I were to sketch this, it'd look like this. So here's 4, there's 4, and right there is negative 4. So with this function right here for g, this is just a semicircle, and there is no discontinuities here at all. So we are continuous everywhere, because if I were to draw this semicircle, if I don't pick up my pencil or my pen, whatever I have, it's going to be continuous. We're only going to see discontinuities really on piecewise functions. There's possible discontinuities, or anything with a ratio in it, so any type of fraction. That's going to be our biggest ones that we're going to see some issues with. So this one is going to be continuous on its domain. There are no discontinuities. Okay, and then the next one here, it helps if I factor that top one. So let's go ahead and factor the top, and I will factor the bottom here. So I'm going to double bubble to help me factor. It has to be x and x. In order to get 12, I'm going to get 6 and 2, so how about plus 6 minus 2 on the bottom here. How does that factor? It's going to be x and x. It has to be 6 and 1. Both are plus. See if you notice here, I'm going to have the x plus 6's cancel out, so I'm going to have a hole at x equals negative 6. And right here, since the x plus 1 is still there, I'm going to have a vertical asymptote at x equals negative 1. So let's identify these discontinuity types. So I'm going to be, for the negative 6, since it's a hole, that is known as a removable. I don't know if that's how you spell removable. If I'm wrong, please let me know in the comments. Or if I'm right, please let me know in the comments. Discontinuity at x equals negative 6, and we have an infinite discontinuity. I can't even spell infinite. Continuity at x equals negative 1. All right, and last part right there, C. We're going to have some domain issues here, because if we were to take out the pieces of this, it's nice to know that ln of x has to be positive everywhere where x is. So our domain here for ln of x is going to be that x has to be greater than or equal to 0. Okay, so let's just kind of keep that in the back of our brain here. As I go ahead and go through this and I factor it, top does not factor at all. Bottom does factor. I'm going to get x and 4 and 5. How about a minus 4? How about a plus 5 right there? So I'm going to have issues at 4 and negative 5. I'm going to omit negative 5 because I have my domain issue here. There's no way I can plug in any negative numbers into this function. So I have a domain issue there, so I only have a vertical asymptote at x equals 4, which means that that is going to be my infinite discontinuity at x equals 4. So go ahead and make sure that you like and subscribe and ring that bell if you want to see more videos like this to help you out with your learning.